Hello everyone, my name is Mike and I'm sharing with you my list of 10 techniques to improve your group delay measurements on frequency converting devices with embedded local oscillators. So for example, I'm talking about devices like this MyTech satellite block down converter. This particular device takes a 20 gigahertz signal in and mixes it down to about 1 gigahertz using an embedded local oscillator that operates at 18.75 gigahertz. I want to measure the group delay of devices like this, and I have a list of 10 ways for you to improve your measurement accuracy and to make your measurements easier and faster than ever before. Now, of course, in this series of videos, I'm using the Rohde and Schwarz ZNA vector network analyzer. This network analyzer was introduced about 1 year ago, and it has been optimized for making measurements on frequency converting devices like that MyTech satellite block down converter. So in particular, I'm going to use option K9. This is our two-tone technique, which we use to measure group delay on frequency converting devices. If you want more information on this option, you can refer to application note 1EZ81. This is on our website, and it goes into great detail about how the two-tone technique works for measuring group delay. Now, as I said, I have 10 ideas for making this measurement more accurate, and each idea has a dedicated video where I go through how I optimize the parameter and what the effects are as we make the improvements. This is the summary video. I'm at the end. We've already gone through all 10 ideas, and we've gone from a starting trace that was very noisy to, at the beginning of video number 1, to the end of video number 10, where we have a very smooth trace which really accurately measures our device under test. So I want to show you that before and after comparison, and then give you a brief review of the 10 different things that we did so that you can decide if it's worth going back and watching the individual videos. Okay, so let's take a look at the instrument right now. Again, I'm going to do like I've been doing in the videos. I'm going to take advantage of this GPIB Explorer tool, and I'm going to pull up a script file that is my summary script file. This script file is going to compare my starting point to my ending point. So the beginning of video number 1 to the ending of video number 10. So it asked me to connect the calibration mixer, which I've done, and it's calibrated the measurement. Now, in addition, I'm taking one shortcut. I've also applied the S-parameter calibration to this second channel. So I'm taking advantage of S-parameter calibration plus mixer calibration. This is the most exciting feature on my top 10 list, and it's the feature I covered in video number 10. So I'm not going to go through it again right here. You can go back and look at that video, but this is definitely something worth looking at. This is the best thing we have right now for making our group delay measurements as accurate as possible. So I've calibrated the two channels. Next, I need to connect to the device under test, and I can see directly then the difference from when I started in video number 1 to the conclusion at the end of video number 2 with respect to how accurate and how clean is my measurement. So let's connect to the output of the device under test and the input. All right, and now let's go to the scale and couple these two measurements so that they track each other, and then bring them down on screen. And let's zoom in a little bit. Oops, wrong way, this way. And so now we can see the two measurements. So this top channel was our measurement at the beginning of video number 1, where we did not optimize any parameters. We used the preset settings of the instrument. We just took them, whatever they were, and used them without considering what they do. And this bottom trace is the result after we've applied all 10 techniques, and we've reduced the error after calibration down to the order of less than 50 picoseconds. We've gotten a really flat trace after calibration. We've applied S-parameter correction, so we're more immune to mismatch. We've also applied attenuators at the end of the cable to settle down the effect of mismatch. So number 10, or after 10 steps, this is what we get, which is a really smooth, nice looking trace. This ripple in this trace, I'm really actually convinced that it's due to the device under test. It's not something in our calibrated channel. So this measurement is as good as it can be. We're not employing any tricks or any cheating. We're not smoothing the trace or anything like that. And so just to kind of make the point, let's also overlay this trace so we can see this trace on top of our starting point trace. So this was the beginning, video number 1, and the video number 10. And then just a quick recap, the 10 different things we did to make the improvements. And again, there's a video for each one. So the first one was automate your measurements because it documents all your settings. You'll never forget a setting, and it's so easy to do with the built-in tools on the ZNA that it's something I've done in video 1, and then I carried that forward through all the videos. And in addition to that, it shows every setting. So we will share, you can have a copy of these script files that I created. Just contact your local account manager if it's not available with the video, and they'll get a copy for you. Or I hope that they're distributed with the videos so that you can duplicate these measurements directly on your own. You don't have to wonder what setting was used for this or that. It's all in the script file. Video number 2 talked about selecting the optimal way to create the two-tone signal. We have 4 different methods for combining 2 ports to make a two-tone signal. That's all covered in video number 2. In number 3, we talked about optimizing power level, which is important both for the measuring port of the VNA, the device under test, and the transmitting port of the VNA. We have to keep all of these devices below their compression point and well above their noise floor if we want to make good measurements. So that's the topic of video number 4. Number 5, we looked at how the IF bandwidth affects our measurement, so we can trade off measurement speed with trace noise. And in number 6, we talked about averaging. So IF bandwidth trade-offs and averaging trade-offs, they are very similar, they are related to each other, and we can use both those techniques to improve our measurement, especially during calibration. If you wonder what I mean by that, go take a look at that video. Number 7, we talked about LO tracking. So we have devices under test with embedded local oscillators. It's possible that that local oscillator is at the wrong frequency. Either it drifted away from where it belongs, or we weren't sure where it belonged in the first place. LO tracking will tell you where it is, and it will let you correct for that error so that you can make an accurate measurement, even though the yellow is drifting. That was video number 8. Video number 9, we talked about this mismatch that occurs. Up to now, the calibration technique on the ZNA had always been a normalization technique, and we use attenuators at the ends of the cables to minimize the effect of mismatch during this normalization calibration. And in particular, when we switch from calibrating to measuring the device under test, and we get a different reflection coefficient, that messes up our measurement if we don't use attenuators. So video number 9, we talk about how attenuators can help reduce the mismatch. But the absolute best thing I have on my list, on my top 10 list, is number 10, which is to use S parameter error correction in addition to everything else that we've mentioned up to now. So for the first time now, in firmware release 2.0 that just came out on the ZNA, we now have S parameter error correction. You know what? Let me check that. I don't want to make a mistake. I think it might actually be, it's actually released. It is 2.0. Okay, good. So 2.0 has vector correction for the K9 group delay measurement. And so this actually further mitigates the effects of mismatch in addition to what we can do with the attenuators. And it is the reason we can get such a clean trace when we're measuring the frequency converting group delay of a device that has an embedded local oscillator. So this has been quite a journey. It's been 11 videos. I've had a blast showing you the different things we can do to optimize the measurements. I hope there was something in there for you to learn. I hope you got something out of it and found it interesting. Again, my name is Mike. I've really enjoyed it. And let's look forward to seeing a future video where I can go through another topic in detail like this. All right, until then, take care.